Hey there, AP Chemistry students. We're now at section 3.4 on the ideal gas law. So our learning objective here is to explain the relationship between the macroscopic properties of a sample of gas or mixture of gases using the ideal gas law. So a quick review on gases. More so than any other state of matter, they are defined by the motion of particles. This is considering their high kinetic energy and lack of cohesive forces. So in a solid, you have your atoms or molecules, and they're all held in place, and they're not moving around. They're attracted to each other by either inter or intramolecular forces, but they aren't able to move. That is, unless you raise the temperature and give them a much more kinetic energy, which causes them to vibrate and then eventually break free of those cohesive forces. However, they don't break free completely when you go from solid to liquid. Once it melts, now the particles are able to move around each other, and they have just enough kinetic energy that they can break free from the cohesive forces temporarily to move and then, make new cohesive forces with another particle. And that process just continues over and over. If you give it even more kinetic energy by raising the temperature, you'll eventually boil and get a gas. And this is when you've completely overcome all of the cohesive forces through having a very high kinetic energy. They're able to pull away from each other and move around independently. So when we talk about the macroscopic properties of a gas, we're usually describing the pressure, temperature, or volume of the gas. And these might seem like obvious concepts, but let's think about what that means at a molecular level. So the pressure is the exertion of particles through either collisions with the container or other particles. So if we imagine this substance here, we have these little black dots that represent either molecules or atoms, and they're moving fast with a lot of kinetic energy, and they're going to be colliding with the walls of the container, and they're also going to be colliding with each other. A good way to think about this is that, say you have a balloon in your hand and you try to put pressure on the balloon. If you try to squeeze it, it's going to put pressure back because the gas molecules within the balloon are colliding with the surface of the balloon itself. So the temperature is the average kinetic energy of the particles. Basically, how fast they're moving or with how much energy they're moving with, because different masses of particles will cause different speeds. We'll talk about that in 3.5. But overall, it's the average kinetic energy of the particles. Not all the particles are going to be moving with the exact same amount of energy. You're going to have a little bit of a gradient with that. And we'll talk about that in 3.5 as well. The volume is going to be the space in which the gas is contained. So if you think about these particles moving around on their own, they're just going to keep moving unless something is going to be in its way, like the walls of the container. So gases are going to expand to fit whatever container it's in. And some containers are flexible, meaning they can stretch and better accommodate the volume if it's to increase, like a balloon, for example. Though some are rigid, like a jar, and they will have a set amount of volume. So no matter how much gas you put in it, it's going to be the same amount of volume. That is, unless you have so much pressure in it that the container itself breaks. But for when we see the words rigid container in some sort of problem, we can always assume that the volume is going to be constant. All right. So whenever we're trying to quantitatively analyze gases, there are some certain assumptions that we need to make in order for the calculations to be clean. And we do this, we consider all gases to be what are called ideal gases. So the two assumptions that we use, one is that the volume of the individual gas particles are negligible compared to the volume that they're contained within. Um, Say you were to imagine a 1 mole sample of helium. You would want to assume that that has the same amount of volume as a 1 mole sample of xenon if they're both gases. Even though xenon is a much bigger atom, since these particles are sort of moving around on their own, they're not really interacting with each other. The volumes of the individual particles are not going to matter very much. And then two, that the gas particles do not have any intermolecular forces. If you have two gas particles that move by each other in a gas, if they get really close to each other that they might collide, they might have like a really temporarily short attraction to each other that might change the momentum of the particles and then therefore change the collision of the particles. So we assume that no intermolecular forces are at play here that might, affect the pressure of the gas like that. And in most circumstances, these assumptions are true. There are a couple conditions in which ideal gases start to deviate from having what we call ideal behavior, but we'll talk about that in 3.6. So when we're measuring the physical properties of gases, there's usually an established set of conditions that we sort of normalize things by called standard temperature and pressure, or STP. Standard temperature and pressure is 273.15 Kelvin. This is a unit of temperature, which is equivalent to 0 degrees Celsius, and then 1 atmosphere of pressure, which is the average sea level pressure. That's why we call it 1 atmosphere, because if you're standing at sea level, you have a single atmosphere above you exerting pressure on you. Um, if you wanted to convert the temperature in Kelvin to Celsius and vice versa, the relationship is that the temperature in Kelvin is equal to the degrees Celsius plus 273.15. That's why 0 Celsius is equal to 273.15. This is going to be important in chemistry to know how to convert things into Kelvin, because if we're going to be using temperature in equations, we need what's called an absolute scale for temperature. Absolute scales are kind of like absolute values in math where we have no negative values, because if you throw a negative sign into an equation, that's going to affect everything else in the equation. And the only difference between negative 10 Celsius and positive 10 Celsius is 20 degrees. There's nothing inherently special about that negative sign. So whenever we're doing math with temperatures in chemistry, we want to put them into Kelvin so that we avoid that negative problem. Also, 0 degrees Celsius is a temperature, but if you plug 0 into math, you end up canceling out everything basically. So yeah, we need to use all of our temperature values in Kelvin and not Celsius. So one important thing about being at STP is it defines what the molar volume of a gas is. I talked about molar volume briefly before, but it's kind of like molar mass, but instead of being grams per mole, it's the volume per mole. It's the liters per mole. And under standard temperature and pressure conditions, 1 mole of any gas, it doesn't matter what it is going to have the same volume, which is 22.4 liters. So we describe the molar volume of a gas being 22.4 liters per 1 mole. And this goes into our ideal gas law assumption, where like 1 mole of helium and 1 mole of xenon are going to be occupying the same amount of space despite the size difference in those particles. So just as a little thought thing, if you had half of a mole of gas, how much volume would you expect it to have? I guess considering standard temperature and pressure. Well, if 1 mole occupies 22.4 liters, we would assume that half of a mole occupies half of that, which would be 11.2. All right, and then the last thing I want to talk about before we actually get into the ideal gas law itself is the common pressure units. So temperature is going to be in Kelvin in most cases. The volume is going to be in liters in most cases. Sometimes they'll give us milliliters when we want to convert it to liters. But then pressure seems to come in a wide variety of units. The most common you're probably going to see is atmospheres. And like I said before, 1 atmosphere is the average sea level pressure. There's another unit called kilopascals, where 1 atmosphere is equal to 101.3 kilopascals. And then there's also millimeters of mercury and torr, which are basically the same unit. They have the same value. I don't know why these two different units were named after each or were equal to each other when they have different names. They come from the concept of a barometer. This is sort of an old school pressure measurer where you have a pool of mercury that the atmosphere is pushing on, and depending on what the pressure is, the mercury will be pushed up this tube, and this tube is going to have like a ruler on it basically that measures how high it goes up the tube. So the more pressure, the more the mercury is going to go up the tube here. And this was invented by some Italian physicist named Torricelli. So that's why we have torrs. But for all intents and purposes, torr and millimeters of mercury are the same. And if you ever need to convert between them, you can just use dimensional analysis. So if you had 0.5 atmospheres, you could multiply that by 101.3 kilopascals over 1 atmosphere, and you'd end up with a value in kilopascals. All right, so now let's talk about the ideal gas law. So this is an important equation in chemistry when we're relating different properties of a gas. And it relates the pressure, volume, and temperature, and the amount of moles of the gas. And this allows us to solve for one of the variables if we know the other three. So say we didn't know the pressure of the gas, but we knew the volume it was contained in, we knew how many moles if there was, and we knew the temperature, we could solve for the pressure. I didn't mention R here. R is a constant, and that's going to be dependent on what pressure unit you're using, since the pressure units are variable. For atmospheres, it's going to be 0.08206 liters times atmospheres over mole times Kelvin. The units are kind of complicated. I'm going to talk about that in just a sec. But since the relationship between atmospheres and kilopascals are two different numbers, the constant is going to be 8.314 for kilopascals, and then also 62.36 if you're using torr or millimeters of mercury. So these units are kind of complicated, liters times atmospheres over mole times Kelvin, but the constant needs to have these units so that if you are solving for one of the unknowns, that you can give it the units it needs and cancel out all of the others. So like in the example I gave before where we were calculating the pressure, the volume is going to be in liters, the N is going to be in moles, and the T is going to be in Kelvin. I need this value in liters times atmospheres over mole times K so that the K can cancel out the K in the denominator here. The moles can cancel out the mole in the denominator there. And when I divide both sides by the volume will cancel out with the volume in the numerator, and we'll end up with just the units of atmosphere, which will be the units that we want if we're solving for the pressure. A good way of remembering this, or at least the arrangement of the units, is to solve the equation for R, which will give you pressure times volume over moles times temperature, which are the correct arrangement of units. Also, if you know the constant for one of the pressure units, say the one for atmosphere, you can convert it to the constant for the other pressure units using dimensional analysis, using the ratio between them. So here's how we can calculate the constant for kilopascals by using the kilopascal to atmosphere ratio. And then here's the equation for millimeters of mercury. You'll end up with the same values. All right, so let's do some practice with this. So let's calculate how many moles of a gas are contained in a sample with a volume of 1.5 liters, a pressure of 2 atmospheres, and a temperature of 100 degrees Celsius. And since we're using atmospheres as our pressure unit, we're going to use 0.08206 as our constant value. So whenever we're working with equations in chemistry, I always recommend that you solve it symbolically first. What I mean by solving it symbolically is figuring out what variable you're solving for and then do it with just the letters. So in this case, we were calculating how many moles. So that means we're solving for N. So I can solve the ideal gas law for N, where I'll have PV over RT. And then I can take my values from the problem and just plug them in and do all of the math all at once. So I'll have 2 atmospheres times 1.5 liters divided by the constant and divided by the temperature in Kelvin. You'll notice that even though we were given 100 degrees Celsius, that I turned it into Kelvin by adding 273.15. And then you'll see that the units start to work out because atmosphere is going to cancel out with atmospheres there, liters is going to cancel out liters there, Kelvin's going to cancel out Kelvin there, and then we're going to have 1 over moles, which is the same thing as just moles. And then when I multiply all the values on top and divide the ones on the bottom, I end up with 0.098 moles. You also notice that I used 2 significant figures here since the values that I was given in the problem, the measurements I was given in the problem, were limited to 2 sig figs. Let's do another one. At what temperature in degrees Celsius will 0.0105 moles of a gas in a rigid 500 milliliter container have a pressure of 205 kilopascals? So let's solve it symbolically first. PV is equal to nRT. We're solving for T, so we'll divide both sides by nR. So the temperature is going to be equal to the pressure times the volume over the moles times the constant. Then I could plug in all the values. You'll notice here that I went from 500 milliliters to 0.5 liters. It's important that you convert it here since the constant has units of liters in it. And if this is still in milliliters, those units are not going to cancel and the math is not going to work out correctly. So when I calculate it, I get 1,174.15 degrees Kelvin. But we want the temperature in degrees Celsius. So we're going to subtract 273.15 and we're going to end up with 901 degrees Celsius. So based off of the equation, we know a couple things about the relationship between pressure, volume, and temperature. We know that pressure and volume have an inverse relationship, which we can see on a graph here. As the volume increases, the pressure starts to decrease. And we know that just based off of the equation, because if I'm at constant moles and constant temperature, if one of these goes up, the other is going to have to go down. So if the volume is going to increase, the gas is going to get more spread out and it's going to exert less pressure. And vice versa. If I decrease the volume, the container is going to be smaller and there's going to be more collision. There's going to be more exertion. For pressure and volume, with temperature, it's a direct relationship because, say, the volume stays the same. If the temperature goes up, the pressure is also going to have to go up. And that makes a lot of sense because if you're increasing the temperature, you're increasing the kinetic energy of the particles. That's going to lead to more collisions. And also, if you're in a rigid or a non-rigid container, one that can expand, say like a balloon, if you increase the temperature, those particles are going to move fast, exert more pressure on the container itself, which is then going to expand the volume by having the pressure exerting against the surface of the balloon. And we can see that here we have a direct relationship between temperature and volume, direct relationship between temperature and pressure. And this last graph here is just showing more about the inverse nature of volume and pressure by plotting the inverse of pressure times, or as a function of the volume. I don't have a graph for it here, but pressure and volume also have a direct relationship with moles. And this makes a lot of sense because if you have 1 mole of a gas in a balloon and then you put another mole in there, it's going to exert more pressure. There's going to be more collisions with the gas itself. So as you increase the amount of stuff, that's also going to increase the pressure and volume. And vice versa, if you're decreasing the amount of stuff, it's going to shrink. All right. One last thing about the ideal gas law itself. It could also be used to relate density and the molar mass of a gas. You might be asked to do something in a problem related to the density of a gas, or asked to calculate the density at a certain amount of conditions. And this is done through a sort of substitution. So we know that PV is equal to nRT, and we know that the density is equal to the mass of a substance over the volume of the substance. And we have a V in the ideal gas law as well. So if we solve for V, so we have mass over density, and then plug that into the equation, now I have pressure times mass over density is equal to the moles times RT. I could do another little trick here where I switch D and N by dividing both sides by N and multiplying both sides by D, and then I end up with M over N, mass over moles, which is just the molar mass of a substance. So then I can rearrange it to say that the molar mass of the substance is going to be equal to the density times the constant times the temperature divided by the pressure. So as a practice, let's calculate what the density of carbon dioxide would be at standard temperature and pressure. So since I'm solving for D in this case, I'm going to have the molar mass times the pressure over the constant times the temperature. I can calculate the molar mass of carbon dioxide from the periodic table. So it's 44.01 grams per mole. We're at STP, so it's going to be 1 atmosphere and 273.15 Kelvin. And then since I'm using atmospheres, I'm going to use the atmospheric constant. And then I do all the math, and I ended up with 1.96 grams per liter. And you can see that the units work out correctly because atmosphere is going to cancel out atmospheres, moles are going to cancel out moles, Kelvin's going to cancel out Kelvin, and then we're going to have grams over liters. All right, so this is a different formula that is also related to ideal gases called Dalton's law. And Dalton's law is used to determine the partial pressure of ideal gases in a mixture or the total pressure given the partial pressures. So it looks like this, where the total pressure of a system is going to be equal to the sum of the individual things that make it up if it's a mixture. A good example of that is air. Air is a mixture of oxygen, nitrogen, argon, water vapor, and carbon dioxide. And each of them are going to exert their own pressure on the container, in this case, the atmosphere, or say like a balloon if we pump some air into it. And you can see that these values are probably in kilopascals because you can see the 101.3 101.3 kilopascals, which is equal to 1 atmosphere, one unit of the average sea level pressure. So they all have different amounts in the atmosphere, so they're also going to exert different pressures. But the partial pressures of the individual gases are always going to sum up to the total pressure of the system. And the partial pressures themselves are defined by the following relationship, where the partial pressure, say the pressure of gas A, is going to be equal to the total pressure of the system times what we call the mole fraction, which is usually X with the subscript of whatever we're identifying as the partial pressure of. So if I'm measuring the partial pressure of A, I'm going to calculate the mole fraction of A by dividing the moles of A, the total moles of A, by the total moles of gas as a whole. So let's do a practice with that. Say we have 1 mole of nitrogen gas, a half of a mole of xenon gas, and 3 moles of methane. And we know that the total pressure of this combination is 2 atmospheres, and we want to know what the partial pressure of all of the 3 gases are. So we can do that by calculating the mole fraction of each and then multiplying that by the total pressure. So we had 1 plus 0.05 plus 3, that's 4.5 total moles of gas. And if I have 2 atmospheres total, I can multiply the mole fraction of each by the pressure to get the partial pressure. So for nitrogen, there was 1 mole of it. So I had 1 mole divided by 4.5. That's going to give me the mole fraction. And then I multiply that by the total pressure, and I end up with 0.444 atmospheres. I can do the same for xenon and methane. Divide their moles by the total moles and then multiply by the total pressure, and then I get partial pressures for each of these. And you'll notice that if I try to add these back up, I end up with 2 atmospheres again. I add up to the total pressure of the system. And this should always be true. The partial pressure should always add up to the total pressure. Another example that will definitely come up in the lab assignment that I want to do in class is if we're calculating, if we're doing an experiment where we're collecting gas over water. This is a common practice when we're collecting gases from a chemical reaction. We use like a vessel that's sort of dunked in the water. And if we have a reaction going on here, bubbles are going to be created, and the bubbles are going to float up and then start to fill a space in this container within. So if we want to know what the pressure of the gas in the vessel is, we can assume that the gas in the vessel is going to be both the gas we're collecting, which in this case is hydrogen, and then water vapor due to the fact that there's a vapor pressure to the water, and the water is going to be escaping in small amounts and filling this space. We know that by the way it's set up, that the pressure inside this container should be equal to the pressure outside of this container. And if it's open, that means the atmosphere is pushing down on it, which means that the pressure inside the container should also be equal to atmospheric pressure. So let's say that the atmospheric pressure outside is 784 torr. We also know that the vapor pressure of the water at the current temperature is 23.5 torr. This is something you can look up. There's usually tables that relate the pressure, sorry, not the pressure, the temperature of water to its vapor pressure. And I think you'll see one in the lab assignment. We can use this to calculate the pressure of just the hydrogen by knowing that the pressure inside is equal to the pressure outside. What that ends up looking like is we have the total pressure of the system, which is equal to the atmospheric pressure, being equal to the sum of the pressure from the water vapor and the pressure from the hydrogen gas. And we know what the value of the vapor pressure of water is at this temperature. So then we could just subtract this from the atmospheric pressure, and then we end up with 761 torr, which will be equal to the partial pressure of just the hydrogen gas that's being collected. So that's all I have to talk about for this, for ideal gas laws, and I'll see you in section 3.5.